This method is going to combine the idea of a volume of a rotating solid with the concept of the area between two curves. So I'm going to click this video example here to kind of illustrate what I'm talking about, because this video is much better than anything I could come up with regarding how to visualize this. So this is from C. Schmidt 1968 on YouTube, and we'll kind of show you just at least the visual of it. So this is my y equals the square root of x that I'm graphing here, and y equals 1/10 x, which we'll graph next. And you can see that we've got this particular curve. We're going between x equals 0 and x equals 4, and we're going to shade in the region. And we know how to find the area of that region. But now what we're going to do is we're going to take that region and rotate it around the x-axis. And you can see that it forms this hole here in the middle. Okay, it's got a shape kind of with the hole. And when you take out a cross-section of it, it's a disc with a hole through. So if you've ever done any kind of construction or building, you know that this is called a washer. So that's what we're going to use to simulate the, or to estimate the volume of this particular shape. Is we're going to look at imagining that there are infinitely many washers forming it. So there's just basically a gap in the between the axis of revolution and the rectangle. So instead of a disk, we're forming a washer, and this is now called the washer method. So what you end up having is an outer radius and an inner radius, but the width is still going to be the width of a disk. So the volume of this particular washer would be the volume of the outer washer minus the volume of the inner washer. So that's pi r squared w minus pi little r squared w. And if you factor out the pi and the w, you get this. And if we extend this definite integral and use a definite integral, we let r of x represent the outer radius and little r of x represent the inner radius, then we can find the volume as such. So we know that to find the volume of the outer radius, we would have pi times the integral from a to b of r of x squared dx, because that's the disk part, and then the inner radius volume, we would be subtracting pi times the integral from a to b of little r of x squared dx. And this is just two integrals that are subtracted, so we know that we can combine that into a single integral and have r of x squared minus little r of x squared, all with respect to x. So that is the washer method. So I'm actually going to evaluate the integral that was shown in the video. So square root of x was the outer radius, so this is going to be my capital R of x. The 1/10 x is going to be my little r of x, and we're going to go from x equals 0 to x equals 4. So v here will be the integral, pi times the integral from a to b of r of x squared minus little r of x squared. So this will be pi times the integral from 0 to 4 of the square root of x squared minus 1/10 x squared, all with respect to x. So I'm going to start off by simplifying things a little bit. This gives me x. This gives me 1 over 100 x squared, all with respect to x. And when I integrate that, I get x squared over 2 minus 1 over 300 x cubed from 0 to 4. And my pi is going to get multiplied by, first we'll have 4 squared over 2 minus 1 over 300 times 4 cubed. And then we're going to subtract 0 squared over 2 minus 1 over 300 times 0 cubed. So we get, if you multiply all this out and add together, 584 over 75 pi, and that's going to be units cubed. So that would be the volume of the solid that we saw in the video. Now this example is an interesting one because it's got one portion that can be estimated using discs and one portion that's going to be estimated using washers. So notice here I've got this section right here that's just basically a rectangle being revolved, and then I've got this section that's going to have the hollow in the middle. So I also notice that I am revolving around a vertical axis of symmetry, or axis of revolution, so I want to have horizontal rectangles, which means everything needs to be in terms of y instead of x. So y is equal to x squared plus 1. Another way to say that is y minus 1 equals x squared, or x equals plus or minus the square root of y minus 1. Now if you look at the actual graph though, we're only interested in the positive half of that because everything is to the right of x equals 0. So for the easy portion, for this rectangle down, r is going to be equal to 1, from 0 to 1. And for this other portion up here, the outer radius r is 1, and the inner radius is the square root of y minus 1, because if you were to measure this distance here, that's what you would get. So I'm going to have two separate integrals that are going to form each of these. So we'll call this part A and we'll call this part B. So A is going to be found by just integrating from y equals 0 to y equals 1 of 1 squared dy. That's my A. And then B is going to be found by integrating from 1 to 2, because those are the bounds you were given. And we're going to have the capital R squared minus the little r squared with respect to y. So that's going to be my B region. And of course, if you want the volume of the whole shape, you just add it together. So basically it's this cylinder, but in the middle somewhere we've carved this parabola type shape out of it. So I'm going to be integrating from 0 to 1 of 1 dy. And then over here, I'm going to be integrating from 1 to 2. This is going to be 1 minus y minus 1 when you square it. Here we get y from 0 to 1. That one's pretty easy. I'm going to simplify this one a little bit, distribute the negative. And this is really 2 minus y. So here we have pi times 1 minus 0. This one will be 2y minus y squared over 2 from 1 to 2. So we have pi plus pi times 2 times 2 minus 2 squared over 2, all minus 2 times 1 minus 1 squared over 2. So this gives me pi plus pi times 4 minus 2, which is just 2, minus 3 halves. So we have 1 plus 1 half, which is 3 halves pi. So that's 3 halves pi units cubed. And that would be the volume of that solid. Now keep in mind that we've been looking at videos about how to find volumes of solids with circular cross sections, meaning if you take a slice through the shape, then you would get a circle. But you can find the volume of solids with any known cross section if you know how to find the area of the cross section. So with this one, for example, your cross sections are rectangles, and as long as you can evaluate the area of that, the volume is going to be the integral from a to b of that area with respect to x. So we've been doing that, it's just our area has been pi r squared. But if it was something else, all you would have to do is plug in whatever that formula is.